Okay, cool.
So, good evening everyone. This week's NISER talk is being given by Sneha from Batch 21 on solar physics. Let's welcome. Yeah, it's about solar physics. Let's welcome Sneha.
Thank you. I'm Sneha. I'm from my third year integrated MSc. And I did my research, my internship at Aries and an online internship at the University of Tokyo. And through this, I learned a bit about solar physics, especially one component or one specific problem, which is the coronal heating problem. So in this talk, I will mainly be focusing on, like, first I'll introduce solar physics, and then I will talk about the temperature and density profile of the solar atmosphere. And then there will be a bit of mathematics. So basically that is required for us to understand what is the problem and what are the solutions. So this will be basically I'll be giving an introduction to the basic equations of hydrodynamics and magnetohydrodynamics. And at the end, I will show a few simulations that I have run, like in one of my internships. So solar physics, the sun, right, the closest star. We know a lot about it, like a lot of at least popular science about it. Is there anything that you guys can, first thing that comes to your mind when you think of solar physics or the sun? Magnetism, yes, very important. And yes, now that's what we are going to be probing, like how do we know that it is hot, or how hot is it? So these are a lot of things like nuclear fusion, black body radiation, sunspots, coronal loops. And the interesting fact is that they all have an interplay in the sense that they are interconnected and they affect each other. And hence, we can't study them alone. Now, nuclear fusion gives rise to the energy, and black body radiation is what we observe. And how the black body radiation differs from the ideal black body curve will, through that, we can infer a lot of information. So let's see how we make some solar observations. As I was talking about the black body curve, so uh, we assume in a sense that the sun is a black body. That is, it emits radiations of all wavelengths and in some particular intensity. And now when we fit it to the ideal black body curve, we find that it is actually about 5,000 Kelvin or 6,000 Kelvin. But which part of the sun is 6,000 Kelvin? We'll come to that in some time. And then there's the technique of direct imaging. So Galileo, many of you would have heard that got the direct imaging of sunspots and first found about the sunspots. And then we have the Zeeman splitting, which is a very interesting thing, and very interesting application. That is, when you have magnetic field, your spectral lines will split. And that would split in any case, how much ever is the magnetic field, but it is visible like for such a long distance, whatever intensity that we are able to observe, the resolution is such that only for very high magnetic fields can we observe the Zeeman splitting. And then we have emission lines, which is coming from the corona as well. That is some interesting thing that I'll talk about. And then the heliograph, basically there are some seismic waves inside the sun. So this is going to talk about the density structure inside the sun. Isn't that interesting? Like, we can't go anywhere close to the sun, but then we are able to talk about the density structure inside the sun. That is because of how there are waves that are being reflected across layers. We know that the refractive index and the frequency have some relation. And then lastly, the coronagraph. This is another very important tool for what work that I'm studying right now. So it is to study the corona. It is basically, we can say, it creates false solar eclipse. So the center of the sun has very high intensity radiation. So this high intensity kind of washes out the radiation that's coming from the corona. It's basically that not like the corona is not radiating some light, but it's more like we are not able to resolve what is the intensity that's coming from the corona. Now, during solar eclipse, when the center of the disk is closed, right, is obscured, we are able to see what is the light that's coming from outside the solar disk. Now, to create a fake solar eclipse, we have the coronagraph. And also we have imaging in different spectrums, like different parts of the electromagnetic spectrum, which is shown in the last picture here. So it's very important for us to know the basic structure of the sun. At the core of the sun, we have nuclear fusion happening. This nuclear fusion is going to give rise to some light, right? Because mass is being converted to energy. That energy is actually going to be radiated in the form of gamma rays. But this gamma rays is going to collide with a lot of matter inside the core, and that is called the radiative zone. So basically, there's a lot of absorption and re-emission that's happening. So what happens is that the wavelength decreases. Basically, the energy is being absorbed by a lot of particles, right? And then comes the convection layer, where the energy is being transported through means of convection. So a very common example that's given in this situation is water boiling. So when you have water boiling, you have convection taking place, and you see those bubbles that's coming up, right? So similarly, we can actually see such bubbles called as granulations on the surface of the sun. That is, sorry, of plasma. So basically, the sun is made up of plasma because it's at such high temperatures. So mostly it's plasma, sometimes it's kind of ionized gas. And so you have the photosphere. That is the first, that is the topmost layer, you could say, of the sun. Basically, the surface of the sun is the photosphere. As for why we decide this to be the radius, there are a lot of things that goes into it. There are different kinds of ways to define your radius. I wouldn't be going into that right now. And so the first bottommost layer of your atmosphere is the photosphere, and then comes the chromosphere, this part. It's a very thin region. And after the chromosphere comes the corona. So why are we actually dividing it into such parts, right? There should be some basis on which it's being divided. So let's look at the temperature. And before that, I would like you all to think about one thing. The sun is a source of energy. It's radiating some heat. So there is some temperature everywhere, assume. So if I'm able to measure the temperature far from the sun, now at steps, do you think that the temperature will go down? Will it go up? It will go down? It will go down, right? Why? Because by second law of thermodynamics, you need an energy source for it to again go up. So when you're going away from, for the flux to be maintained, when you're going away from the energy source, the temperature will be decreasing. But look at this graph. It is initially decreasing, indeed, and then it reaches a minimum, and then it starts to rise. And this part is actually the chromosphere, where it has this slight rise is the chromosphere. And then there comes the transition region, where it's the transition between the chromosphere and corona. Rather, it's because the temperature is transitioning from a kind of 10,000 Kelvin all the way up to 10 power 6 Kelvin, which is a million Kelvin. So, and that is happening in a very short range. So that's like about 200, 300 kilometers width. So why is this happening? What is the source of energy, right? So this is known as the coronal heating problem, as to what is the source of this energy. That's because of the pressure. You know, you need enough pressure for the quantum tunneling to happen. So it has to be so close to each other, the hydrogen ions, right? So it should be so close to each other that for quantum tunneling to happen, they have to be very close. And that kind of pressure is found only at the center of the sun. But as the sun will start aging, there is the unconventional kind of a expansion and contraction that will be happening at different layers, and you'll start having helium fusion at the center and some another shell of hydrogen fusion that will be happening at another layer of the. What is the exact potential for quantum tunneling? Oh, the electrostatic forces, right? Because it's proton and proton, then they are going to repel. Now you have to overcome the Coulomb barrier, basically. So in order for you to overcome the Coulomb barrier, if you assume some kind of a Maxwellian distribution of your protons, right, you have to go to the very end, because we know that the temperature is not like infinity or something. There is some finite temperature. So it's like it has some velocity limits, right? So it has some velocity limits. So if you're having the Maxwellian distribution, you were expecting something from the very far off tail to actually expect some kind of fusion. That is not enough to source the sun, right? So you need quantum tunneling into the picture to increase the probability of this, of the nuclear fusion happening. And why? This is not fission, huh? Right. Hmm. There are a few chains, like you have some kinds of proton-proton chains or carbon-carbon chains, but I did not get your point. It's not like that. Oh no, that the reason is because that it's not sufficient. The pressure conditions over there is not sufficient for fusion to happen in the outer layers. Once it starts happening, right, that's where you'll have another shell of hydrogen burning. So as of now, the pressure is not sufficient for it. Energy is being emitted, but the pressure is not sufficient. What should become uniform? Fusion, right? No, because at the other regions you do not have such high pressure to counteract, right? Because now see, you're saying that there is some energy that is coming, okay, but that energy is not sufficient for, you know, it's just going to push, like the energy is moving outwards, right? So it's just going to push your gas particles away. But the whole point that is what is keeping it inside, what is keeping the fusion reaction contained? The gravity. The gravity is so high, that's why fusion is happening. Let's first understand that part. That's why getting nuclear fusion on Earth is so tough, because it's. Oh no, it's not negligible. It's keeping the sun together. It's keeping the sun together. It's not negligible. We are talking about astronomical scales. Gravity between the two of us is negligible. Okay, I'll proceed because if we have more doubts about this, we'll talk later. Because I have a lot of slides. Huh? Okay, so now moving on. Yeah, now it comes to mathematical terms. I'll be mathematical equations I'm going to throw around, but it's just so that you get in the groove. These are equations that most of you would have already come across, but because we'll be using this in the further calculations, I'm just going to talk about these. First is fluid approximation. Okay, so what can be considered a fluid and when can we apply fluid dynamics to it, and the basic equations governing it, and about plasma. Plasma, that's what we need ultimately. We want to see, the aim of this is to see how plasma responds to the external situation, the external environment. Okay, so first, when is something called a fluid, it needs to have sufficiently high number of particles, and there should be frequent collisions. Okay, so now there are two kinds of variables. You have kinematical and thermodynamical variables. Velocity, density, pressure, these are important variables. Okay, temperature and pressure are kind of related. So yeah, and now a small aside note over here that there are two kinds of derivatives, time derivatives. One is the total time derivative, one is the partial time derivative. The partial time derivative is basically when the observer is in the rest frame of whatever you're talking about, whatever system you're talking about. And but when that is basically this red person over here. But if you're the blue person over here, you're observing the system also moving in time, and there is some reaction happening in the system that's also going in time. This does not require relativistic effects. Okay, like let's not get confused. Even under Galilean transformation, this holds. So you have static and co-moving observers. Okay, so these are the degrees of freedom. First, the density. Then you have three components of velocity and pressure. Okay, so for each of these, to find these out, to characterize these, you will need a set of equations, which is what we'll be looking into right now. The continuity equation of the oh yeah, so basically that is to see when do we say that some collision is frequent enough. So everything is relative in the sense that now if the basically that the mean free path of the particles is much lesser than the size of system, is equivalent to saying that the rate at which the collisions are happening is much faster than whatever this process is happening in the system. So that's the point. Because when I use the word frequent, there is some kind of a relative term that comes into picture. When is something called frequent? When is it frequent enough? So to characterize that, you will need this condition. Right. Yes, that's very right. So we are not. That's when we are actually considering that they are acting as a union together, and those individual interactions don't actually matter. So that's actually correct. So those basically we are separating the length scales by saying that frequent collisions means that I don't have to care about it right now. Yeah. So the continuity equation. Basically, the continuity equation says that whatever is the change in mass inside the volume is equal to whatever is the mass that is going outside the surface. So this is the mathematical derivation of it, but I want you all to just focus on this particular equation. This is called the mass conservation equation. Sorry, I didn't. Huh. Right. Yeah, so over there we can't use fluid dynamics to completely. We are talking now onwards. We are talking about the solar atmosphere, where we can this fluid approximation will hold only over there. We can't use the fluid approximation over there. I don't think so. And also, do 1 second. Sorry, the conservation of yeah, that will become conservation of mass and energy. Basically, that will be you'll go into the relativistic picture, so it will be conservation of mass is equal to conservation of energy. Yeah, you can't assume that it's fluid. Yeah, so that's the point. Plasma can't always have a. Okay. Okay, I'm sorry. I think that what Vasant is saying is that whatever is the mass that is going out, we are also accounting for the energy. Once we account for the energy, the fluid dynamics is as well applicable at the center of the sun. Right. That will be energy density. So next is the Euler equation, or basically the conservation of momentum in a sense, or the third law of Newton. This says that whatever is the change in momentum inside a certain volume, that is because of the pressure that is acting on the surface. So this is the final equation that I would like you all to focus on. So over here, rho is basically the mass density, v is the average velocity, and P is the pressure, and F is some kind of an external force per unit mass, right? external force per unit mass. So now say if gravity is also there in the picture, just G vector. Your acceleration due to gravity is F vector. Okay. So from this we can also now, if I am going to characterize what is F vector as basically shear, viscosity and gravity, then I would get my Navier-Stokes equation. That was just an aside, we won't use it now. Sorry. Oh, about the length scales are we talking? Huh. Right. Yes. So actually, it's a very interesting question because I will be talking about shear velocity very soon. The thing is that when you have magnetic field also over here, so in the solar atmosphere, we so have a condition that there can be two adjacent regions which have actually different velocities. So now when you have such different velocities and you do have shear viscosity, if shear viscosity we are considering it, then it will play a role. Basically the whole it's not that it is against the length scales. The thing is that there can be adjacent regions which is separated by some velocity difference. Shear, yeah, right. So there will be shear over there. There will be a shearing effect. Um, as for more relevant, I don't know the context as to what you mean by relevant, but okay. So that again has its um, contexts in the sense that now when I'm talking about magnetic pressure, then expansion and compression will come into picture more than shear. But then when I'm talking about magnetic tension, that is whether I can twist the magnetic field lines or not, then shear will come into the picture. Okay, so now kind of trying to bring us back to the topic, talking about plasma, right? We were trying to characterize plasma. So let me quickly define what is plasma. It is a collection of charged particles, and it could also have neutral particles, which meets the following criteria. First, that it is quasi-neutral in nature. That is, on a large scale, it is almost neutral. And second, that it shows collective behavior. That is, once again, as we were talking about collisions that doesn't actually bother the outcome of your result. Similarly, over here, the collective behavior is one due to that, and second, that the length scales of your system is much larger than whatever collisions are happening, and secondly, that there is electromagnetic interactions that come into picture. Okay, so the electromagnetic interactions is basically that now you have some charges moving, and you have magnetic field of the sun, so that is going to affect the charges. One charge will be moving at some velocity, that will be affected. Once that starts to accelerate or that starts to move, it will have some magnetic field of its own. That magnetic field will in turn affect another charge's motion. So basically there is an interplay of the electromagnetic forces between the charges. So it will cascade, and then basically there is a long range effect of the electromagnetic forces. So I think we already discussed about this, that the length scales are always important. When we talk about a system, what are the processes that would contribute to the system? To understand that, we will need to know the length scales. Now, we have plasma. We talked about fluid dynamics. Is that sufficient? Not exactly, because we have not accounted for the magnetic field. Now, if plasma is there, I'm going to apply fluid dynamics, that would be fine. But the issue is that there would be magnetic field. How is this magnetic field actually going to be consistent with your Maxwell's equations? That will be covered in magnetohydrodynamics, and also when there's an external magnetic field, how is it going to behave? So first, the features of MHD. There is a plasma approximation that it is a fluid and that it's in quasi-equilibrium, basically that I can define temperature, pressure locally. And second, that Ohm's law is at least instantaneously being satisfied, and this can be relaxed in some situations. I do not know which situations exactly though. And that this is the microscopic form of Ohm's law, because we'll be talking about electric field, current density, and magnetic fields. And second, that the plasma will be considered to be neutral. And basically, MHD is just the interplay of hydrodynamic interactions and electromagnetic interactions. So what is ideal MHD? When there is no electrical resistance. So when I'm considering an ideal magnetohydrodynamic system, there is no electrical resistance. This gives rise to a very popular theorem, which is called the Alfvén flux freezing theorem. So this says that, I'm just going to say it in general right now, I might talk a bit about it later. So basically that if you move your plasma, and then your magnetic field lines will move along with it, and vice versa. Basically that if you move your magnetic fields, that's going to ultimately move your plasma along with it, right? And keep in mind that will happen when there is no electrical resistance, which is a good approximation in many cases. So now there is no electrical resistance, meaning the first thing that comes to our mind is conductor, right? And we know that in conductors, electric field is 0. So we are like, okay, electric field is 0. Now we are talking about charges and everything. How does that make sense? So firstly, we talk about in which frame. Once again, I'll finish this one. So first we talk about in which frame is the electric field 0. Some of us would have already done this in special relativity, that the electric field actually changes from frame to frame, right? So I'm going to talk about the rest frame. In the rest frame, the electric field is 0. Now, this is the observer, this frame. Okay, so now if I put E vector is 0, my parallel component goes to 0. Okay, and my perpendicular component goes to 0, and hence what I'm observing will be different. So it's just going this, which is going to be 0. So then one more question that might arise right now is, okay, electric field is 0, then does that mean that my current density is also 0? Like I just said that Ohm's law should be satisfied, right? But no, because the electrical conductivity is infinity, because I'm considering no electrical resistance. That means that electrical conductivity is infinity in an ideal situation. But obviously nothing is so ideal. We have some large value for conductivity, and so for electrical resistance, which is very, very low basically. Okay, so the effect of the electric field will basically be observed through the effect of charge density, of the current density, sorry. So we finally, when I put these two components to 0, I get this equation relating my electric field and my magnetic and velocity. Section is that I have 8, sorry, actually not 8 plus 1, 8 plus 1, right. We have 8 plus 1 equations if we actually count the vector components to be separate. Then the one, why have I written it separately? That's basically the constraint. So that is the del dot B is 0, and that gives rise to 7 degrees of freedom. Now is the kind of interesting part, that is linear wave analysis. Okay, so what I've shown over here is true even for a hydrodynamic case or a fluid dynamic case. So if I want to see the velocity of sound, then I can do this and try to get what is the velocity of sounds for some very small perturbations. So in linear wave analysis, basically I'll be considering some small perturbations to the terms of the degrees of freedom, basically. So for mass density, for pressure, for velocity, each of them I have taken some small perturbation, and then I have, and using the mass and momentum conservation laws, we can derive these equations which will give rise to these solutions. But what is interesting is this c square factor. This c square, we know, is basically the velocity with which the medium is going to transport some kind of an information. So now we do not have any magnetic field perturbations, right? If now I have magnetic field perturbation, then what is going to happen? That's the interesting case. I'm going to make some assumptions in order to derive this equation, that is basically take my magnetic field to be lying along some particular coordinate, and so is the wave propagation direction. But ultimately, what we obtain is this. This is omega square. From here, we can actually infer what is the wave velocity. This is what is going to play a very important role. The calculations are pretty analogous to what we did for the non-magnetic case, except that it is more involved, so I'm not showing that in detail. It can be done in the same way. So the thing about this is called as the Alfvén wave. So Alfvén wave is just one of the different your plasma, okay, where you're going a plasma which follows the MHD equations. Other wave modes are like there are things like slow modes, fast modes, which I am not completely aware of, so I'm not going to make a comment on that. Okay, so this is basically the speed with which some energy is being transported through your plasma, okay, along the direction of your magnetic field, but the particles are oscillating perpendicular to the directions of the magnetic field. Yeah, you can imagine them like pressure waves. You can imagine them like pressure waves. At least I imagine them like that, but I'm not completely sure. I have not confirmed with anyone. So, what about the rho naught factor over here then? Yeah, yeah. The particles are moving. It's a longitudinal wave, so it will be moving in the perpendicular direction. The energy is propagating in a certain direction, in the perpendicular. Okay, so that's why we call. Mm-hmm. Hmm. Okay. Right. 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 No, no, it's the change in your magnetic field, basically. Your magnetic field lines will exist, but it's the change in your magnetic field that that can have some finite value. Basically, see now, even when you are doing, we know that okay, there is some energy contained in the fields, right? Now I'm one of the right, that is the if I want to extract that energy, it will come out as electromagnetic waves. That's right. But then I also think that over here, basically, that a change in your magnetic field might give rise to electromagnetic waves. But that is again, but the change in itself need not happen at the speed of light. Does that make sense? Huh. the particles are oscillating such that the energy is being transported, if I'm not wrong. Right, Vasant? Yeah. But it's transporting the energy along the direction of the fields. Yeah. So you need your uh-huh. So right, that is actually the group velocity. You do have phase velocity terms also which you can derive. Okay, so now we are coming back to the problem statement, which is the coronal. Yeah, d omega bt. So now we'll come back to the coronal heating problem. Uh, to just review what the actual problem was that there is the sharp rise in temperature near the corona, right? So let's see what are the things that, firstly, how did we find that there is this kind of a sharp rise in the temperature, and secondly, what are the proposed mechanisms to solve this puzzle? First is that it starts with, okay, realizing that there is a corona that, as I told, happened during solar eclipse. And second, the existence of Fraunhofer lines. Basically, they are absorption lines which tell you about the chemical composition of what is between your energy source and your observation. Right? It's basically some light is passing through, whatever is being absorbed um, by the particles, it will come off. So what happened is that, yeah, as I had mentioned before, the uh, you know the spectra is being studied in different ways, in the sense that, firstly, okay, you have your spectra for, okay, you have your absorption lines, you have your emission lines. Firstly, that it's a black body, it will be, we are assuming that it's giving out a continuum, right? So but the point that there is a shift, there could be a Doppler shift, and that is because of the high energy of the electrons that is between where you're observing and the energy source. This high energy electron in the corona. We'll be, now I'm telling it backwards, but the thing is that we first observe the shift, the broadening. There are two things. Firstly, there is the shift of your spectra. Secondly, there is the broadening or of your spectrum of whatever are the lines that you're seeing. So uh, these two will talk about what is the density and what is the temperature, right? One is about the density, one is about the temperature. Temperature is proportional to your velocity, right? So, right. So now when we saw this kind of, we expect Fraunhofer lines to be observed, but we did not observe Fraunhofer lines because it's being completely washed out by some particles that's there. So we kind of get an idea that there should be such high energetic particles between your energy source and you, such that the line broadening is so much that you're not able to observe your absorption lines. So that is the and this, if you theoretically calculate, you get it to be around 1 million Kelvin, right? And secondly, in the outer corona, you see that, okay, there is some interplanetary dust and there are some absorption lines. That's nice. And then you have the emission corona, wherein you see that there are quite a few different types, I guess a few dozen types of emission lines that we observe. And this emission lines, we thought initially, actually scientists were so puzzled by this emission line because they hadn't seen something like this before. So they thought that there is a new element, coronium, right? But then later on, someone realized, I forgot who exactly, realized that no, it's not a new element, but actually very highly ionized iron and nickel, which is giving rise to such emission. So yeah, basically for such high ionization, you need very high temperature. Now, if you work backwards, again you get to know that this temperature will be of the order of 1,000,000 Kelvin. So this again corroborates with the puzzle that, okay, the corona is actually so hot, and that there is a sharp rise in the temperature is actually coming from your Fraunhofer lines. As to where exactly you stop seeing the Fraunhofer lines, things on those lines. And okay, so this is just an aside kind of a thing. What we see, what are the structures in the corona? So one structure at least that I know of is the coronal loops. So these loops have a start point and end point. It's rooted in your photosphere. And what are the foot points? That's going to be an interesting thing. Any guesses for what would be the start and stop of your coronal loops? Something that, yeah. Oh, no, no, no. Okay, let's. I don't mean it in that sense. Now you can see over here that the loop is, it's a coronal loop that's just starting like this, and it's ending by your photosphere. The end of the loop is the photosphere layer. Okay, but then now say that this whole thing, which is the start and which is the end? Which one do you think it is? Huh, that's right. I'm not talking about the direction. I'm asking like what could be the foot points. It's something that you all have. Huh? Oh, yeah, yeah. Okay, it's written, I guess. I also didn't see that. Right. It's the sunspots, basically. Okay, so sunspots are actually regions of very high magnetic field. That's why it actually, you can see it as a sunspot, that it doesn't have very high temperature because it has very high magnetic field. Okay, so now let's talk about the approach of how we are trying to solve the coronal heating problem. It's widely accepted and agreed upon by the scientists that the source of this energy is from the convection layer of the sun that we had talked about before. And the heating mechanism is due to some kind of turbulence, because turbulence gives rise to heating. So this turbulence can be either due to MHD waves or due to something called as magnetic reconnection, which I won't be touching upon in this talk. And so comes the first proposal. Okay, that is the dampening of the Alphen waves, and this dampening is actually causing the heating of the corona. But okay, fine. There could be like collisions with another, say, of some plasma particles during the transport. There are collisions, and hence you're able to see the dampening of waves. But then, is it so easy to say that okay, dampening can happen because of collisions? No, because actually what it is that if you're considering only the collisions to cause dampening, then about 3 solar radius for it to completely to get to the heat that you require for to reach 1,000,000 Kelvin. So by estimates, we know that at least this whole dampening process should happen within 2 solar radii, so that it will go, like there is heat conduction downward, there is enough heat conduction downward so that it can create a transition region. Fine. So now let's see. This is some proposal that is there, but is there any evidence to this? Okay, we actually find that the wave start damping at 1.15 solar radii. Okay, so and this observations is coming from spectra. From studying the spectrum, we get to know that okay, the waves are actually starting to damp at this point that is shown over here. This is basically what is your wave amplitude versus the distance from the sun. You would think, okay, why should the wave amplitude actually increase with distance? That is basically because with distance your density is decreasing. So the Alphen wave amplitude, if you remember the equation, it depends on your density. So when your density is decreasing, you will want your Alphen wave amplitude to increase. Mm. No, no, we know that there are Alphen waves. You can observe Alphen waves. Oh, this is the graph of the Alpine wave amplitude versus the distance from the center of the sun. Now, okay, so fine. So basically, this is, as I told you, it's from the observations of the spectrum, right? Now, if I am going to observe the spectrum and I'm going to conclude something, it's going to be, the spectrum is ultimately affected by these points. So there are some lines corresponding to these points, and that somehow gives me the point that, okay, this is the Alpine wave amplitude. But then as for the exact precise calculations as to how to go from the spectral lines to you know, finding the Alpine wave amplitude, basically through the density, in fact, because their density affects the shift of your spectrum. So that we derived it, right? In the derivation we saw. Shall I? It's as it goes as 1 over. Right. Uh, Actually, as for what is the exact process that they have done conducted to do this, I'm not sure. But one guess I can give is this: the farther you're going away from the sun, the lesser you know about the sun. So whatever is your backward calculation that you're doing, I guess would have more errors. That is a guess I'm having, because you know a little bit more about what is closer to the sun. Yeah, these are experimental points. Experimental points that is corresponding to the spectral lines. So these, you're deriving it from the spectrum. Your spectrum will have the, no. I'm also saying that, hmm, no, but what are you going to observe? You will observe intensity, right? So your intensity will have, okay, there is some error that is coming from that. But from intensity, you're changing it to wave amplitude, right? So there's some calculation involved. That calculation can have errors based on what you know, right? That's, I think, since it's a sorry? Huh. No, I'm assuming, I'm guessing that might be we are giving an error to what could be the error in your theoretical values. Because basically, okay, now I'll just tell one small thing, that is getting to know what is the actual wavelength of the Alpine wave that is propagating is actually very tough. Okay, basically, when you're doing your simulations, you assume a lot of wavelengths and then see, okay, which is corresponding to your actual graph. So, and the difference is in order of zero 0.1 megameters. Your Alpine wave amplitudes. What is the, you, so to guess what is the Alpine wave amplitude that is actually being observed is kind of tough. So that, I think, could be a reason. Okay. So now we see that, okay, the density is basically for energy conservation, as I had mentioned. When density decreases, your undamped amplitude should actually increase, but then you see a decrease. So we know that there is dampening at about 1.1 to 1.2 solar radius. So what is causing this damping? There are some different reasons which has been proposed. One is phase mixing, which I'm not going to touch upon. The other thing is density fluctuations and reflection of the waves. Okay, so the two of them in an interplay will give rise to turbulence. I will come to that. I will come to that point. So the density fluctuations can occur due to a lot of things. That, okay, from the photosphere, there is some kind of an eruption. There is a compressive mode which is passing by. and the whole physics of which, when I'm not completely sure of, but there are a lot of things because the solar atmosphere is actually so dynamic. There could be a lot of reasons to give rise to the density fluctuations. But what happens when there is a density fluctuation, right? Firstly, how do I observe? Okay, so before that, as she mentioned, what does the density fluctuation have to do with your reflection? Basically, that your density fluctuations implies that there is a change in refractive index. When there's a change in refractive index, there is a part which is going to get reflected, a part which is going to propagate. This is actually also called as, which it could give rise to something called as parametric instability. I will come to that in some time. So, what this is yet another observation, because since the best observable is intensity, now I can work backwards and say my intensity is related to density, and from my density I can, if I know what is the intensity fluctuation, then I can know what is my density fluctuation. And as you also have told that, okay, there is a lot of systematic errors, all those will be accounted for, and then going beyond those fluctuations, what is the leftover fluctuation, that is what we are going to account for, right? So what we see in this graph is that, interestingly, there is a density fluctuation at between 1.1 and 1.2 solar radii. So we can say that, okay, the alpha wave damping which happened between 1.1 and 1.2 solar radii is somehow connected to the density fluctuations which is happening between 1.1 and 1.2 solar radii, which is starting over there. It's not happening only in that region, it's starting there. It happens even further. And also, we cannot consider this part of the graph because there is a lot of noise. Okay. One point five two. Sorry. Yeah, but then that's where we are going to see, okay, now what is, I am subtracting out what are all the systematic and statistical errors that's there, or the statistical fluctuations. That is what I have denoted on this side, basically, right? And then I'm trying to calculate what is this term. What you have mentioned, okay, I have, so the error bars are actually small because I am able to somehow detect what is the detected noise or the counting statistics, because the statistical error or whatever is the real fluctuations in the corona, assuming that I'm able to do this, I'm actually getting what is my the density fluctuation that I'm looking for, basically that the fluctuations that is happening at the corona, right? Right. Right. Yeah. Hmm. Yes, yes. It as well could be. I just simply circle this region, but then you could. Uh-huh. Okay, might be. Yeah, I'm from this me circling this. I'm just trying to show that, okay, it's between 1.1 and 1.2 that there is the fluctuations, and beyond that your error bars are too high. But yeah, as he rightly pointed out, I shouldn't have circled this region. It would have been more right for me to circle out something in between, because there the error bars are also lower. That's near the photosphere. So I think because near the photosphere you do have some density fluctuations because it's very close to the convective layer. Now we go to the proposed solutions. That there is parametric instability that I talked about before. That parametric instability is basically the kind of nonlinear interaction that happens between different wave modes, which gives rise to some daughter waves. Okay, so now what is happening is, when I have a density fluctuation, I have reflected waves. Now there is also an incoming wave. So there's an incoming wave, there's an outgoing wave. These two waves will interact. Now this interaction is non-linear in nature, so it is going to give rise to different wave modes, and there is ultimately it will give rise to turbulence, and that will cause heating. So yeah, basically this is what I have emphasized over here. And secondly, there are simulations which show that alpha wave heating increases in the presence of density fluctuations. So you can run simulations to verify that. So now let's delve into the setup and a particular situation, a particular solution, and with that we'll almost be done, right? So this is the photosphere and about chromosphere corona. At the photosphere, you have the beta parameter, which I had mentioned before, that is thermal pressure to magnetic pressure, is actually high. So basically, your thermal is high, so your magnetic field is kind of confined. But then up above, your beta, your magnetic pressure is basically lower than your thermal pressure. So you're seeing that the magnetic field lines expand. So these are called like magnetic flux tubes, which expand. Um, so what happens over here is that this is in one region of the solar atmosphere, this is in another region of the solar atmosphere, so they could have different temperatures, different densities, yeah, different, basically that will affect your alpha wave speed as well, right, and even different magnetic field, very importantly. So now when I have such things which is going off, right, but then your direction will be all maintained. It'll conserve all the laws that we have just studied right now, all the equations. But what we see is that there is an interface that is being formed. And this comes back to that very first question that we saw, that okay, this is the interface where there can be adjacent regions in the solar atmosphere which has different velocities, which can have different magnetic fields, also densities. There are a lot of things that can be. Right. Yeah, the fluctuations are with respect to time. Time. Oh, no. Now I'm not going to talk about the density fluctuations. Now I'm looking at a different setup. That was one of it. So that was me just trying to say that, yeah, there are, experimental evidence and also simulation evidence, which is going to talk about how density fluctuations and alpha waves go hand in hand. Now I'm talking about a different kind of a fluctuation, okay? Because the coronal heating problem, it's widely studied for like about 50 years now, and there are a lot of proposed mechanisms. We can't say that it's only one mechanism which can give rise to heating. In fact, there could be many mechanisms combined effect which would give rise to this heating. Okay, so now I'm going to talk about another particular kind of instability which can give rise to this heating. So at this interface, you can have a difference in densities and velocities. So yeah, we could say, okay, why wouldn't it reach equilibrium all of a sudden? Because as we had come across before, the magnetic field, the transport along the magnetic field is very high, but then transport across the magnetic field is low. Basically, because that will involve a lot of other twisting or torsions. So for such a transport to happen, we need some kind of perturbation. So one instability which is very well known and is present in a lot of places, from the skies on Earth to Jupiter, is the Kelvin-Helmholtz instability. So you have two layers of fluids parallel to each other which have a relative velocity between them. So when there is such a situation and you apply a perturbation to it in a perpendicular direction, or which has a component along the perpendicular direction, then this, uh, you know, basically this can give rise to an instability, and whether the instability will continue to grow or will, and become turbulent, or whether it will die down will depend on your setup. And an important factor that you have to consider in an instability is vorticity. Vorticity is basically the curl of your velocity field. And why is it important? Because when your the curl of your velocity field will actually give rise to basically vortexes, which you have seen, and this is a major center for energy cascading to happen. I will come to that point in a while. Before that, I will explain what is KHI. So assume that, okay, there were two layers of fluids. One is, this is the relative motion that we are seeing. Okay, one is flowing in one direction, the other is flowing in the opposite direction. And see, this is a perturbation that was applied to it. Now what happens is that by Bernoulli's theorem, we know that the velocity over here should be faster as compared to over here and here. And similarly, the velocity is faster over here as compared to here, right? So this gives rise, and also we know that this means that the pressure over here, where the velocity is high, is low. So the pressure over here is low, and the pressure over here is low, and so is it over here. So now this creates a pressure gradient. When there's a pressure gradient, your instability starts growing along that direction. So now, yeah, I can just show it over here. So you have two fluids with different velocities. Now this is the the first perturbation that we give, and then this starts with the instability, because now you have the velocity to actually be pointing in this direction, but as this starts moving up, it will have a component along that direction as well. So now your the velocity will start having a curl, right? So this is actually some kind of a vortex creation, and this is basically the Kelvin-Helmholtz instability. So the energy cascading is going to happen from larger vortices to smaller vortices, and this is again a nonlinear interaction. So what happens is that at larger vortices will give rise to smaller vortices, and at very small vortex lengths, your viscosity will come into picture. And when viscosity is there, considerable amount is there, heating is going to happen, right? So that is basically the outline of why there can be a damping mechanism and ultimately turbulence and heating. So yeah, till now whatever I had shown about the Kelvin-Helmholtz instability did not have magnetic fields in it, right? So what is special about the magnetic field? We again go back to what we saw as magnetic tension, right? So when you have magnetic tension, it's going to see to it that when you have a perturbation like a twist, it comes back to its equilibrium form. So but when the perturbation is too high or the magnetic field is too low, then we start observing the Kelvin-Helmholtz instability. And what happens in this case is that we again have, when you have this kind of a perturbation, and KHI starts setting in, that will ultimately lead to a perturbation in magnetic field. When you have a perturbation in the magnetic field, we know that alpha waves can be formed. Now, alpha waves are very good transporters of energy, right? So now this is going to transport your energy that was previously stored as might be heat, or it can go and deposit that energy elsewhere as well. So this is just a quick point that what is the velocity difference between the two layers is actually equal to the alpha wave velocity. So what we observe is that there is some kind of a resonance that happens between, so when there is a velocity difference which is equal to the alpha wave velocity, there is some kind of a resonance that happens, and hence the turbulence is achieved much faster. So now last part, that is the simulations that I have run using the software AMR VAC, and I used ParaView to view the images, to view the simulations. These are just one or two that I have shown, not many. Okay, okay, 1 second. Yeah, so sorry, I'll start it again. So the first one is, let's first check whether AMR VAC works, right? That if I don't have a shear velocity, I should not be getting KHI. So this should, now you can see that it's on repeat mode, okay? So basically you are able to see the formation of something that is basically the perturbation I'm giving, but there is no KHI that's being formed. And next is with shear velocity. Yeah, so we can see that there is some kind of KHI that's being formed, and also ultimately that can lead to turbulence. Now, with gravity case, okay, now in the first one, basically they are both the same situations. One is just a slowed down version, because when there is gravity, things happen very fast. So the gravity is in the negative x direction. So I will just show one quick thing that if everyone can see. This is your coronal loop, okay? Firstly, I'm assuming that, okay, I let it be a semicircle kind of a thing. Now, obviously, this is the coronal loop. I'm flattening it out, and that is what I'm trying to simulate. So, when I'm flattening it out, basically, what is in this direction, right? That would be remaining in the x direction, but what is in this direction is actually the y direction. So, when I'm okay, right? So, when I have this, when I'm flattening it out into a cylinder, right? I'm going to see that my gravity is going to act in this direction, and in this direction. Is this point fine? Because this is going to correspond to the top layer, and there is no gravity along the x direction. And the bottommost point is going to talk about, so you have gravity over here and you have gravity in this direction, which if you actually take it out, they'll be pointing in different opposite directions, and hence this is the gravity that I would like to simulate, which I do for the MHT case. Over here, I just want to show that because of the absence of magnetic field, the formation of the instabilities or the growth of the instabilities is very fast. So I did not do that over here. So I'll finish this point over here itself. Okay. So now if I want to have my gravity in the x direction, right? I will, right? So now in the x direction, I will require it to be in this way. This is the length of your, basically the pixels of your simulation, the domains of your simulation. Okay. So along this length, how would I want my gravity to be? It will be at the minimum because it's an opposite direction, and it will be at the maximum in the other direction, and at the center it should be 0. And this is basically negative of cosine. That is yeah, that's kind of the assumption that at least that I have made in my simulation, that this would go as a negative of cosine. What I'm not including in the simulation is accounting for curvature and aspects on those lines. I'm not accounting for that, right? Sorry. No, I'm not saying it's not constant. I'm just saying that this is, all of this is going to experience gravity like this, but I'm flattening it out. In this form, gravity is constant. But now when I'm going to change it, basically just look at the end points and you can interpolate the in between points. Over here, at the top of the coronal tube, you will see that, okay, the gravity is only in the negative y direction. And so the y component over here and over here will be 0. No, no. Fine. Basically, see, if I'm going to put it up over here, just this part, okay, now there is gravity in this direction just for this part, right? Now I'm going to make it like this, right? I'm turning it so it will now face in this direction. I can do the same thing for that, for each element, and I will obtain this. So similarly for the y component, I will have a negative sign, right? Yeah, only thing is that I did not want to give any particular direction some special significance. So the point remains that your total gravitational acceleration will be the same, right? So if I add it up now, this will be cos, and the other one will be sine along the y direction, right? So this one will be maximum over here, and at the ends there will be zero. The gravity in the y direction, the y component of the gravity at the ends will be zero, and at the center will be maximum or maximum in magnitude. So basically we will have a negative sign, right? So basically, and now I'll want sine square plus cos square to give me 1. So at each point it's going to experience the same gravitational force. Okay, so but for this simulation, this was actually for the MHD simulation. For this simulation, I have just considered gravity in the negative x direction. So you can see how fast it is running. That's one thing. But I will go out of this mode because I'm not able to. Yeah. So with gravity, yeah. So you can see how now the signs of the Kelvin-Helmholtz instability being there is overpowered by your gravity in itself, right? Now let's see how it behaves in this situation. Gravity is a very important fact when it comes to instabilities. The growth of turbulence, like the growth of an instability into turbulence in the presence of gravity is very highly likely as compared to in the non-gravity situation. That's what we also is an issue that we face in fusion reactors, because it's on Earth we are also having the instabilities. But okay, never mind about that. So this is the MHD simulation, where in the first one it's just a sheer velocity. Yeah, so both of them are running for the same time. All the simulations that has been shown till now are running for the same time. But we can see how slowly there is the development and how small the vortices are. It's not giving rise to further vortices as we had seen in the previous cases. You could see that there are different vortices that are coming into picture. So that is because of the effect of magnetic field. So when you have magnetic field, it kind of provides a resistance. And finally, in the presence of gravity, yeah, um, basically it's like your gravity is overpowering whatever is there. But then the Kelvin-Helmholtz instability in itself, basically this line is not enough to cause turbulence in itself. But then also I will say that one very important fact over here is that these simulations can't be corresponding, are not corresponding to the solar situations. Over there you have different kinds of magnetic fields, you have different gravitationally stratified coronal loops, which I am not doing over here. This is just to show the difference between the KHI development in a hydrodynamic case and in a magnetohydrodynamic case. And with that, I come to an end of this talk. Thank you. Any